Let's ponder RL circuits. An RL circuit has a resistor, an inductor, a battery. Okay, we've got a switch in the middle whereby we can either connect to the battery or not connect to the battery. So if we consider, first of all, closing that switch to A, if we close that switch to A, we put the resistor, the inductor, and the battery into the circuit. If we want to analyze this, we're going to look at the loop rule. In our loop rule, the battery voltage is going to be EMF. The resistor, that's going to be an I times R, and the inductor, an L di dt. We know the total voltage is around a closed loop is going to be 0. Now what we need to figure out is what the signs are here. Your battery is supplying voltage, so it's going to be a positive. Your resistor is dissipating, so that's going to be a negative. And your inductor is storing, so that's always also going to go in as a negative. In that resisting, that's going to suppress or delay the buildup of circuits or buildup of current. And so then what we want to do, our goal here, is to be able to solve for an I of t equation. If I'm going to solve this for an I of t equation, I'm going to need to isolate I. So the first thing I'm going to do is get di dt on one side and then a little bit of algebra to get I alone. So then I'm going to subtract the EMF and add the IR to both sides. So I get negative EMF plus IR is equal to negative L di dt. I'm going to divide the negative L to the other side. That's going to flip my signs. So this will be EMF minus IR over L is equal to di dt. We almost have things isolated. I'm going to take the numerator up here and divide it over and throw the dt up top. So this will be dt over L is equal to di over EMF minus I times R. Now we're ready to integrate both sides. So on the left side, we're integrating with respect to time, so this would be from a 0 to t. On the right side, we're integrating from when the switch is open. There would be 0 current. Up to some period of time t, we would have a current of I. Now, left side is easy to integrate. L is a constant, it pulls out. You're integrating dt, so on the left side you get a t over L. On the right side, to be able to integrate this, we're going to need to integrate by U substitution. So by U sub, I'm going to let U be equal to EMF minus I times R. So then du di, derivative here would be a negative R, and if I solve down for di, then di would be a du over negative R. So then I'm going to substitute that in here for di, and I'm going to bring u over here and replace the EMF minus IR. So then on this side, I'm going to get the integral, we'll worry about the endpoints in just a second. di becomes a du over negative R, and then EMF minus IR becomes a 1 over u. Cleaning this up just a little bit, I'm going to multiply the negative R to the other side because it's a constant, it pulls out. So I get a negative RT over L is equal to the integral of u to the negative first du, giving us a little more room here. Integrating u to the negative first du, that's going to give me a natural log, so I'm going to end up with RT over L is equal to natural log of u. Now putting back in what U was, this is negative RT over L is equal to the natural log of EMF minus IR back to our original endpoints of integration, 0 to I. So plugging in our endpoints of integration, negative RT over L is equal to natural log of EMF minus I times R minus, when you've got a 0 in there, this is going to be the natural log of E. Now, simplifying that down, I'm going to get negative RT over L equals the natural log. Difference of two natural logs becomes the ratio. EMF minus I times R over EMF. Get rid of the natural log by raising to the E, so this is E to the negative RT over L is equal to EMF minus IR over EMF. Now a little bit of algebra to be able to solve down for I, multiplying the EMF to the other side. And now subtracting the EMF and dividing over by the negative R. So this is going to give me negative EMF plus EMF base E to the negative RT over L is equal to negative IR. Dividing the negative R over, this will give me EMF over R plus a negative EMF over R from the negative that was there, base E to the negative RT over L is equal to I, or I of T. So then our final equation here, EMF over R, or voltage over resistance, that's current. So then I'm going to rewrite here, I of T is going to be I max minus that I max base E to the negative RT over L. There's your equation that describes the current buildup as a function of time when you close that switch to A. Oftentimes this I max is denoted as an I naught. Happy pondering.